Welcome to Online Precalculus. This is section 3.4, Exponential and Logarithmic Equations. Our objectives for this section are to use like bases to solve exponential equations, or to use logarithms to solve exponential equations. Then we'll use the definition of a logarithm to solve logarithmic equations, or we'll use the one-to-one property of logarithms to solve a logarithmic equation. Finally, we'll solve applied problems that involve either an exponential or logarithmic equation. So first, what exactly is an exponential equation? And this is an equation containing a variable in the exponent. And you can see here all three of these, and we're going to solve them all. All three of these have variables in the exponent. And there's a couple different techniques that we're going to use to solve these equations, but the easiest technique to use is to realize that some exponential equations can be solved by expressing each side of the equation as a power of the same base. And all exponential functions are one-to-one, so if you have a positive base, which we're always going to use positive bases with exponential expressions. So if you have a positive base and a number other than 1, if you have b to the m power and is equal b to the n, the exponents must be equal to each other. So if you think about this, if we have 2 to the 4th on one side, there is nothing that you can put in the box other than a 4 to make these two sides equal to each other. Now, if the bases weren't equal, then yeah, then we would have different exponents, okay? But if the bases are equal, the exponents must be equal to each other. And we can use that to help us solve exponential equations by expressing each side as a power of the same base. And the way we're going to do it is with this one-to-one property here, we are going to rewrite the equation in the form of some base, some exponent equal to the same base, whatever exponent we want, right? Whatever the problem is telling us. Then we set the exponents equal and solve for the variable. Let's see what it looks like. So in this first problem, I have to rewrite it as two sides, both with the same base. I can just leave the 2, so that's 3x minus 8, but I don't want the 16. This doesn't help me. I don't want to write it as a 4 squared. I want to write it as the same base, a base of 2. And then when I do that, now the exponents are equal to each other. Now we can solve for the variable. Now this is just a linear equation. Add 8 to both sides. So 3x is equal to 12. Divide out the 3, and we get that x is 4. Okay. Next one. I can't make both sides, right? I can't make both sides have a base of 9. 9 to some power is not 27, so that doesn't work. But we can make it into, we can make both sides both have a base of 3. 27 to the, or 3 to the third power is 27. Power to a power means you multiply the exponents together. And 3 squared is 9. Power to a power, multiply the exponents together. So that means 3 times x plus 3 is equal to 2 times x minus 1. Now I solve this just like any other linear equation, right? So this is 3x plus 9 is equal to 2x minus 2. I'm going to do the variable first, subtract that from both sides. I'm going to subtract 9 from both sides to give me negative 11. You can get negative answers. That's fine. Negatives can be exponents. Let's try it again. Same base. Make everything have the same base. So 5, 3x minus 6, and I can turn the 125 into 5 to the third power. So that makes 3x minus 6 equal to 3. Add 6 to both sides. 3x is equal to 9, so x is equal to 3. Okay. For part B, we have, I don't, 4 doesn't turn into an 8 easily, but we can turn both to a base of 2. 2 times 2 times 2 is 8. And 4 squared, 4 squared is 2. So x minus 3. Okay. So this turns into 3 times x plus 2 is equal to 2 times x minus 3. 3x plus 6, 2x minus 6. I'm going to collect the x's first, and we get negative 12. Okay, so make both sides have the same base, set the exponents equal to each other. However, most exponential equations cannot be written so that each side has the same base, like these two. Well, 4 squared is 16, but I don't know how to make a 4 into a 15. And same thing, 10 to the 5th power is 100,000, but there's no way to get 120,000. So we use the inverses. Logarithms are useful in solving these equations. So first, we are going to isolate the exponential expression. In both of those, it's already isolated. Then we are going to take the logarithm of both sides. And we can do this because of the one-to-one property again. So if m and n are positive real numbers, then the logarithms are equal to each other as long as m and n are equal to each other. And these can be functions, right? And we can take the logarithm of both sides. Now, the base that's used for taking the logarithm of both sides of an equation can be anything. It doesn't matter. However, if my equation has something with the base 10 in, I'm going to take the common logarithm. Any other time, we're going to use the natural log on both sides. This is just for consistency and simplicity. Easier to write natural log, only 2 letters, as opposed to a regular logarithm, which is 3 letters. And it also doesn't exclude anyone who does not have a calculator, because we're going to need to use a calculator for all of these. And it doesn't exclude anyone who doesn't have a calculator that can do, say, a log base 4 or a log base 7 or something weird. Okay. So here are my steps to using logarithms to solve exponential equations. First, isolate the exponential expression. Isolate the term with the variable. Then, common log on both sides for base 10, natural log for anything else. Then, we are going to use the power property. We are going to take the exponent and pull it to the front of the expression. Take the exponent, pull it to the front, take the exponent, pull it to the front. And if we have a base of e or 10, the natural log or the regular log just goes away because it is equal to 1. So it just turns into 1 times x, which is just x. Then we solve for the variable. This is going to be the most common way that we are going to solve exponential equations that you can't make have the same base. So let's start with the 4x is equal to 15. Okay? So when I see this, I say, okay, can I make the 4 and the 15 have the same base? And it is no. So I'm going to take the natural log of both sides. Then the exponent gets pulled to the front, and we have the natural log, x times the natural log of 4 is equal to the natural log of 15. The natural log of 4 is just a decimal. Right? Your calculator can tell you what it is, but because it is a decimal, we can divide it out to isolate the variable. So that means x is equal to the natural log of 15 over the natural log of 4. That happens to be the exact answer, the answer in terms of a logarithm. if I plug this into my calculator, as I'm doing right now, it turns into a decimal, which is the approximation of my answer, and I'm going to round it to 5, 3, 4. I'm going to round it to 4 decimal points. Usually that's pretty common, 4 decimal points. Okay. Let's try another one. Now, in part B, we clearly see a base 10. So I could take the natural log, but taking the regular log, the common logarithm, is actually easier because 120,000, and of course we're taking the, right, because these two are equal to each other, like the problem clearly says, the logarithm of both of them is equal to each other because of the one-to-one property. Pull the x to the front, and the log of 10, I don't even have to divide it out because the log of 10 is 1. Okay, so this just cancels. It turns into a 1. And so we have x is equal to the log of 120,000, which in my calculator is 5. It was going to be a little bit bigger than 5, right? The log of 100,000 is 5. 5.0792. Let's try 2 more. Okay, so first, with 5 and 134. Cannot make 5 into 134. I can make it into 125. So now I know my answer is going to be a little bit bigger than 3, but I take the natural log, the natural log of both sides. The x goes to the front, 134, divide out the natural log of 5. Okay, so x is equal to the natural log of 134 over the natural log of 5. That is my exact answer in terms of a logarithm. My decimal answer is going to be 3 point, makes sense, 0432. And again, for part B, I'm going to use the regular logarithm because I see a 10. So I'm going to use the common log of 10x is equal to the log of 8,000. The x comes to the front. The log of 10 just goes away. And so that is my answer. My answer is x is equal to the log of 8,000, which is going to be a little less than 4. Not quite enough room. 3.9031. So with this equation, I have to remember my first step. The first step was to isolate the exponential expression. So there's my exponential expression. There's the term with the exponent in it. I got to get it by itself. So I have to first add 3 to both sides. So this gives me 40. E to the 0.6x is equal to 240. Then divide out the 40 to give me e to the 0.6x is equal to 6. E and 6 don't go together nicely. So I'm just going to take the natural log of both sides. The exponent comes to the front. 0.6x natural log e is going to be equal to the natural log of 6. The natural log of e is equal to 1. So we now have 0.6x is equal to the natural log of 6. Divide both sides by 0.6. And so x is equal to the natural log of 6 divided by 0.6. That is my answer in terms of a logarithm. Natural log of 6 over 0.6 is equal to 2.9863. Okay, and that we have our exact answer. Okay. Let's try another one. Find the solution set and then use a calculator. So we've been doing that anyway. Okay, so 7e to the 2x minus 5 equals 58. Isolate first. So 7e to the 2x is equal to 63. Divide out the 7 and we get e to the 2x is equal to 9. Natural log both sides. Exponent comes to the front. 2x natural log e is equal to the natural log of 9. And then the natural log of e cancels out because it is just 1. And then we're left with 2x equals the natural log of 9. Divide out the 2. So x is equal to natural log of 9 over 2. That is my exact answer. Decimal is going to be the natural log of 9 divided by 2, 1.0986. Next, here is a exponential equation, a little bit harder. It's got variables on both sides, both of which are in the exponents. I cannot make 5 and 4 into the same base. If I could, this question, if this was a 16, this question would be nice and easy. Right? But it's not. So what am I going to do? I have to take the logarithm of both sides, natural log, x minus 2. Natural log of 4, 2x plus 3. That lets the exponents come to the front. But when they do, I need to be sure that we are using parentheses because x minus 2 is the whole exponent. Both of them are in the exponent, right? I don't just want to write, if I write x minus 2 natural log 5, that implies only the 2 is the exponent. Okay. Equals 2x plus 3 natural log 4. I got to get x by itself here. So let me distribute these this expression, right? So let me multiply both by the natural log of 5. So that's x natural log 5 minus 2 natural log 5. And same thing on the right-hand side, plus 3 natural log 4. Then I realize that I want all the x's on the left-hand side. So I'm going to leave this one here, but I'm going to subtract 2x natural log 4 from both sides. Okay. And then I'm going to add 2 natural log 5 to both sides because I only want the left side to have x's because then I can factor it out. Minus 2 natural log 4. And what I'm left with is the natural log of 5 is a decimal. 2 natural log 4 is a decimal. I have a decimal minus a decimal times x. So I can just divide that out. And we get our final answer of x is equal to 2 natural log 5 plus 3 natural log 4 over natural log of 5 minus 2 natural log 4. That is the exact answer. Okay, give me a minute here while I put this into my calculator. Hopefully you have a calculator that you can do more than one logarithm at a time, more than one natural log inside of a fraction. It makes it much simpler to type this in. Okay? Nothing cancels, nothing reduces, right? We just need a calculator and we get an answer of negative 6.3429. Long question, little bit harder problem, but we were able to do it. Let's try one more just like it. And again, it says use a calculator, get the solution set, the logarithm answer, and then a calculator to get the decimal approximation. We were going to do that anyway. Okay, so first, my problem is 2x minus 1 is equal to 7x plus 1. I take the natural log of both sides. That lets me move the exponents to the front. Natural log 7. Distribute 2x natural log 3 minus the natural log of 3 is equal to x natural log 7 plus the natural log of 7. The 2x stays where it is. I'm going to subtract this from both sides. I'm going to add the natural log of 3 to the right side, or to the left side, and to the right side. Oops, that's a 7. And then factor out the x. 2 natural log 3 minus the natural log of 7 is equal to the natural log of 3 plus the natural log of 7. Finally, because this is just a decimal, it can be divided out and canceled. And so x is equal to the natural log of 3 plus the natural log of 7 over 2 natural log 3 minus the natural log of 7. Please don't think you can cancel the 7s because that is not the way fractions work. But, ooh, I forgot a parenthesis. Again, hopefully your calculator can have a way to put this in all at once. And when you do that, you get 12.1144, rounded to 4 decimal points. Okay. Another type of exponential equation that you could run across is something that requires you to use quadratic techniques. So if we had a quadratic, let's just use the same one, minus 4x plus 3. You notice that the quadratic, right, the first term is x squared, the second term is x, the last term has no variable. So the first exponent is always twice as big as the middle one. And if that's true, we can factor it using, right, quadratic techniques. This turns into x minus 3, x minus 1. Well, we can do the same thing over here and factor this, except instead of x and x, the first terms have to multiply to e to the 2x. Well, e to the x times e to the x is e to the 2x. And then if I put the minus 3 and the minus 1 in there, my middle terms add together to negative 4 e to the x as well. I now have a product equal to 0. So I can use the 0 product property to set each piece equal to 0. And so e to the x is equal to 3. Take the natural log of both sides. The x comes to the front. X natural log e cancels because it is 1. And so x is equal to the natural log of 3, which is in decimal 1.0986. And e to the x is equal to 1. The natural log of 1 is just 0. Right? And that cancels out because that comes to the front. The natural log of e is 1. And the natural log of 1 is 0. Hard to see there. Natural log of 1 is 0. Let's try another one. Same again. We're going to do both things. We're going to find the value in terms of e, and we're also earn the value in terms of natural log, and we're also going to find the value in terms of decimal. So e to the 2x minus 8 e to the x plus 7 is equal to 0. I can use my factoring techniques here. So this is going to be e to the x and e to the x. Factors of 7 that add to negative 8 are negative 7 and negative 1. Okay, well, just like the last one, e to the x is going to minus 1 is 0. So e to the x is equal to 1, natural log, and you get x is 0. So the left one is the only one where we need to use a calculator. So e to the x is 7. We take the natural log of both sides. The x comes to the front. X natural log e is equal to the natural log of 7. Cancels. So x is equal to the natural log of 7, which is 1.9459. Okay, so that was about all we have for exponential equations. Let's try a logarithmic equation. And if you couldn't figure this out, a logarithmic equation is an equation containing a variable inside the logarithm. Inside of the logarithm. Okay. Some logarithmic expressions can be expressed in the form of a logarithm, one logarithm, not more than one. If there's more than one, we're going to have to combine them using techniques that we saw in section 3.3. So it's going to be one logarithm equal to a number. If we have one logarithm equal to a number, we can solve this by using the inverse and changing them to exponential form. So the first thing we want to do is write it in the form of one logarithm equal to something. Then we change the logarithm. We use the definition of a logarithm to rewrite it in exponential form, and we turn it into b to the c power equals m. Solve, but be careful with number 4. Because these are logarithms, exponential equations, right? The domain for exponential expressions are all real numbers. However, the domain for a logarithm is not all real numbers. The inside of the logarithm must be positive. So your solution must make the inside of the logarithm a positive number. Let's look at a couple. So this is one logarithm equal to one number. So my first step is to change it to my exponential equation. 4 is the base, 2 is the exponent, and that's equal to the thing inside the logarithm. Now this is very easy to solve. Subtract 3 from both sides, and so x is equal to 13. Part B is not a logarithm equal to a number. It's a product. Get rid of the 3. Divide it out. Instead, you could put the 3 as the exponent, but that makes the problem more complicated, right? Divide it out. Remember, 12 is the exponent. Answers to logarithms are exponents. So you can just change the exponent like this. So this is the natural log of 2x is equal to 4. Now I can use the property of logarithms to change it to an exponential expression. Remember, the base of a natural logarithm is e. The exponent is 4. It's equal to 2x. Divide out the 2. So x is going to be equal to e to the 4th power over 2. That is my exact answer. Again, we can use our calculator to get the approximate answer of 27.2991. Let's try 2 more. Okay. Base exponent equals x to the 4th. So 2 to the 3rd equals x minus 4. So 2 to the 3rd is 8. And we just add 4 to both sides. 12. Again, first step, divide out the number in front of the logarithm. Those cancel. So the natural log of 3x is equal to 2. E squared is equal to 3x. Divide out the 3, and we get x is equal to e squared over 3, which is e squared over 3 in my calculator gives me 2.4630. So again, Logarithmic expressions are defined only for logarithms of positive real numbers. You must always check the proposed solutions of a logarithmic equation in your original and exclude anything that makes the inside of the logarithm a negative number or 0. So again, look at my answers here. This was a 12. Put a 12 in here. We don't get a negative number. We don't get 0. Put a little harder to see here, but put e squared over 3 inside of there, and we don't get a negative number or 0. Okay, it's possible for your answer to be negative, right? If the answer to this logarithm was negative 12, that's okay because it doesn't make the inside of the logarithm negative. It makes it 8. Okay, so even though the solution is negative, it does not mean the the solution is an extraneous solution. Okay, so to rewrite logarithmic expressions in the equivalent exponential form, we also need a single logarithm whose coefficient is 1. Sometimes you have to use the properties of logarithms to condense the logarithms to a single logarithm, okay? Like this. So in order to use the property that we talked about earlier, you need to put these two logarithms together. And the way you do that with the power rule is we multiply. Okay? And so now we can use my one-to-one property, or the rule of definition of a logarithm. 2 to the third power is 8 is equal to x squared minus 7x. Oh, I see a quadratic there. So let's set it equal to 0, which then can be factored to x minus 8, x plus 1. So x is equal to 8, and x is equal to negative 1. Well, that's great, but look carefully at my two solutions. 8 is fine. It plugged into log base 2 of 8, and log base 2 of 8 minus 7, which is 1. But negative 1 cannot go inside of a logarithm. So that answer is extraneous. It is no good. Okay, so you always do have to check back with the original expression to make sure that if you get negative or positive, right, no matter what number you get as a solution, that it actually fits inside of the logarithm. Let's do that again. So we put the two logarithms together, and it turns into, we'll just do this, x squared minus 3x, because I multiply the two together, equals 1. This is a base 10, so it's 10 to the first power, x squared minus 3x. Subtract 10 from both sides, and we get 0, 3x minus 10. Factor, we get x minus 5, x plus 2. So x is equal to 5, which is good. X is equal to negative 2, which is no good. Right? Because just plugging it in to either one, right? Plugging it into either one gives the inside of the logarithm a negative answer. Okay, so those were all problems where we had the logarithm equal to a number. Some logarithmic equations can be expressed in a logarithm equal to another logarithm, where the bases on both sides are the same. And because all logarithmic functions are one-to-one, we can conclude that the inside of the logarithms are equal to each other. Now this, again, only works with a single logarithm with no coefficient equal to another single logarithm with no coefficient. Coefficient is 1 on each side. If this is true, you can write the equation without the logarithms. Log base b of m is equal to log base b of n is equal to m is equal to n. Then solve, and of course, always check your answer. Okay, so again, in this first expression, we don't have a logarithm equal to a logarithm. We have two logarithms equal to a logarithm. I have to put them together. And this is a subtraction, so I put them together with division. Now, because they're both natural logs, they both have the same base, there's one logarithm equal to another logarithm, that means the insides of the logarithms are equal to each other. I'm going to just solve this with a proportion technique, cross multiply. So we go this way, x squared plus 2x this way is equal to 4x plus 3. I see an x squared there. I'm going to set it equal to 0. So x squared minus 2x minus 3 is equal to 0. Factoring this gives me x minus 3, x plus 1. So that means x is equal to 3 and negative 1. Oh, negative 1 works okay there, but it doesn't work in the second one or in the third one. So you got to check every piece to make sure that if you are going to plug a negative in, that it gives you a positive inside of the logarithm. One more of these. Again, natural log of x minus 3 is equal to the natural log. I'm going to put these together. 7x minus 23 over x plus 1. Now I can say that x minus 3 is equal to 7x minus 23 over x plus 1. I'm just going to multiply x plus 1 times both sides. I'm going to FOIL that together. X squared plus x minus 3x, so that's minus 2x minus 3, 7x minus 23 on the right. I'm going to set it equal to 0. So we got x squared minus 9x plus 20 is equal to 0, which factors to x minus 4, x minus 5. So x is equal to 4 and 5. Ooh, they're both positive there. That is a good sign. And it looks like both of them will work. Both are solutions. Okay. So some applications. Let me just check, make sure both of those were the solutions. Yeah, okay, good. So applications just means word problems. So our first applied example provides a mathematical perspective on the old slogan, alcohol and driving do not mix, which is true. In California, 38% of fatal traffic crashes involve drinking and driving. So, and I believe this is true for New Jersey as well. I think New Jersey might be actually a little bit less, maybe 0.07. I'm not sure what the level is. And this textbook is a little older, so I'm not sure what the current level is. Be sure to look, if you are curious, look that up. Okay, so what does this have to do with an exponential equation? Well, there's a formula to tell you the risk of getting into a car accident is modeled by this exponential equation because the variable is in the exponent. Okay, so X is the blood alcohol concentration and R given as a percent is the risk of having a car accident. So I want to know how much does my blood alcohol have to be to have a 17% risk. And you can clearly see that now we are solving an exponential equation. Isolate first, okay? So we get 17 over 6, which is 2.83 is equal to e to the 12.77x. I cannot make those have the same base, so I take the natural log of both sides, and that lets me 2.83 is equal to, that lets me move the exponent to the front, 12.77x natural log of e, which just turns into 1, And now I can divide both sides by 12.77 to give me, now, with a word problem here, right, it doesn't really make a lot of sense to say, oh, the answer is the natural log of 2.83 over 12.77, right? It's better in word problems to actually use your calculator and to get some sort of answer. So you get 0.82. Okay? So even though a 17% risk sounds like it's not that risky, it would still be in California at this time illegal to drive because your blood alcohol would be over 0.8. And you can see from the figure, that sort of makes sense, right? So you got 0.8 right here, and you can see that it's kind of around 17%. Okay? And look at this, 100% blood alcohol, 0.22. So you're about, seems like it should be a little more, but you're a little bit less than halfway there to 100% car accident. Okay, that's a sad question. A more happier question, I guess, is compound interest, right? Because now we're talking about how do you get your money to grow? We know the formula. A is equal to principal times 1 plus the rate over the number of compoundings to the nt power. T is time. The question here is, how long will it take $25,000 to grow to $500,000, 9% compounded monthly? Okay, so we want 500,000. We're going to start with 25,000. 1 plus 0.09 over compounded monthly, so that's 12, to the 12t power, because I want to know time. I want to know how many years this is going to take. All right, let's divide out the 25,000. So 500,000 divided by 25,000 is 20. So we have 20 is equal to, it's best to simplify inside the parentheses. So I'm going to do 1 plus 0.09 over 12, which gives me 1.0075 to the 12t power. Natural log both sides. The exponent can come to the front. So we have the natural log of 20 is equal to 12t natural log of 1.0075. Well, I can get t by itself, right? There's my variable. I can get t by itself by dividing out everything that's a decimal or a number. Well, 12 is a number. I can cancel that out. The natural log of 1.0075 is just another decimal, so I can cancel that out. So we're dividing the natural log of 20 by 12 natural log 1.0075. Okay? And that gives me t of, again, it doesn't make a lot of sense to leave a word problem in terms of a natural logarithm. So we're definitely going to use a calculator for this, 0075, which gives me 33.4, and it doesn't really say, we'll just leave it like that, years, 33.4 years. Okay. So this will be similar to any sort of compound interest formula that you get. Okay. One more application, and that is now a logarithmic equation. How do I know? Well, look, it's got the word log in it. Okay. So we saw this problem earlier, the percentage of adult height attained by a boy who is X years old, and this is in a previous section. It's modeled by this function where X is the boy's age from 5 to 15. And the answer is the percentage of his adult height. So what age, rounded to the nearest year, okay, so we're going to round nearest year, has a boy obtained 85% of his height? 29 plus 48.8 log of X plus 1. Okay. it needs to be a logarithm equal to a number. So we have to isolate. So 85 minus the 29 gives me 56. 48.8 log of x plus 1. Divide out the 48.8. And we get 1.1475 is equal to the log of x plus 1. Okay. Now that it's a logarithm equal to a number, we just take the base, 10. The exponent is equal to x plus 1. Okay. So we just take 10 and raise it to that exponent. We get 14, round to the nearest year, so we can just round that. 14 is equal to x plus 1. So subtract 1, and we get that x is 13 years. So it is 13 years old, rounded to the nearest year, 13 years. So that was section 3.4, exponential and logarithmic equations.